So typically you probably recognize a 1310, 1550 wavelength. We've got the coarse DWDM. So this is we typically see in the metro. So we're talking about channel spacing of 20 nanometers. And typically those systems will use 16 lambdas. There's 18 lambdas defined, 18 channels defined in CWDM from the ITU, but typically systems will use between 8 and 16, right? And they'll keep some of the channels for other stuff. So then we have the dense, so the DWDM. So typically used in long haul today, also seen in pet core and metro, as we see CWDM going elsewhere in some of the markets. So the common spacing, and here we're talking about, when we're talking DWDM, we're talking really in frequency instead of nanometers. So we're talking about 200 gig, 100 gig, and now even 50 gigahertz spacing. So in terms of nanometer, that corresponds to 0.8 nanometer between each channel. So it's not a lot of play, and that comes with some challenge. And as we go on, you'll understand what I mean by that. All right. So if we go back to the ITU bands, and you can see clearly here that CWDM really takes a whole spectrum in terms of the O, E, S, C, and L band. So these are, the channels are broken down. So there's about 18 channels that are broken down with 20 nanometers between each channel across the whole ITU bands. The wide, the WDM, so the wide wavelength, multiplexing wavelength. So I mentioned the 1310, 1550. And we see that typically in the PON environment. So 1310 will be used for voice data upstream, 1490 will be used for the downstream, and we'll have actually a separate channel, the 1550, for the actual video broadcast, and that's often used with the cable MSOs. Okay, and then we have the DWDM, which is basically only covered typically in the C band, and now more and more we're seeing usage in the L band, especially in the very long haul. We want to maximize the number of channels in the fiber, so we actually use also the L band. But typically in the, where we're seeing more now of the DWDM systems and the metro core, it's going to be focused around the C band DWDM wavelength. So what are the differences with regards to the CWDM versus DWDM in terms of technologies? Well, of course, CWDM has a lower capacity, and in terms of costs, it costs us less because the optics required for those are not as stringent in terms of what they require. All right, so it's really used more and more in terms of short-range communication. So the spread between each wavelength is bigger, so it has more tolerances in terms of the actual optics, in terms of the laser. So the drift is more lenient in terms of the lasers as the cycle through heating called cycles. They're effectively relatively compact in terms of equipment compared to what we call the typical DWDM systems and designs, right? From a DWDM standpoint, so like I said, it's more or less partly initially designed for long-haul transmission. So they're really looking at packing very tightly multiple wavelengths, so 32, 64, and even 128 wavelengths into a fiber as we expand in the L band. Typically, we're looking at having amplifiers to boost the signal as it crosses those long-haul distances. And that basically brings a whole set of challenges in terms also of the quality of the signal. So, and we'll touch upon that as we look at the different performance index for DWDM systems. So there's very densely packed in terms of the channels. So it really comes at a very small spacing between the wavelengths. As I said, 100 gigahertz, we're talking only 0.8 nanometers of spacing between the wavelengths. So it really requires a very precise transceivers, high precision, high stability lasers to keep those channels exactly on the target. And that also brings one of the key metrics that you need to be mindful of when you're testing these systems. So if we quickly summarize in terms of what is the differences between them. So CWDM is defined by the wavelength, so the nanometers. So with the channel spacing of 20 nanometers. So looking at 18 channels. With DWDM, well, it's more or less defined by frequency. So there's the ITU channels. So for example, 195.9 terahertz corresponds to roughly 1530 nanometer. 192.2 terahertz corresponds to around 1560 nanometers. But within a few nanometers, you can have multiple channels. So that's why it's simpler to talk about frequency in the DWDM domain. Okay, CWDM, of course, short range, long haul for DWDM, but we're seeing more and more of the DWDM now coming closer with the services where we're actually selling lambdas. So you're basically seeing more and more of that coming closer. Of course, the wider frequency, the wavelengths are spread more apart. Okay, so it's more robust in terms of wavelength drift. So on the DWDM, it's a bit more precision laser, tightly packed wavelength, as we mentioned. So, and typically with CWDM, because it's shorter range, we don't look at the presence of amplifiers in those systems. As with the DWDM, oftentimes, especially with the long haul, of course, we'll have amplifiers, not just one, but many of them. And also a more complex optics as we're routing wavelengths through ROADMs also. All right. So here's a very quick summary view in terms of the presence of the different channels for CWDM. Just looking at typically how that works. We're looking at here a system that has 8 channels to transmit through the CWDM box. It goes through the fiber and then gets demuxed at the other side with the receiving with the receiver end. Right, so we're looking only at 20 nanometers across each of those channels. Okay, so as you can see, plus or minus 6.5 nanometer drift is a lot of headroom in terms of what you can do with regards to that. And that brings us to the possibility of creating and using and leveraging those CWDM networks to add DWDM on top of those. And we call those system hybrid CWDM, DWDM optical networks. And you probably have seen those or heard about those. So how does that look like? Well, it's really a cost-effective way of using what you have already developed and installed in the metro networks. So basically, you're looking at adding and using some of the channels that, like I said, we have 20 nanometers between each wavelength, and the filters are able to tolerate about almost up to 15 nanometers of play. So within 15 nanometers, you can pack, in this example here, we have like 19 wavelength, 19 channels around the 1530 central wavelength of CWDM. And because of that nice filter that enables us to pack, that has high tolerances in terms of up to, like I said, 15 nanometers, you can really jam pack those 19 wavelengths. So through that CW channels, you actually are able to have 19 DWDM signals coming across. So it really has a two level of filtering in there. So also, this is where you can see the benefits of being able to leverage that investment in terms of those CWDM systems, and you can leverage some of those channels and densely packed DWDM boxes for those. All right. All right. Just quickly, Erica, are there any questions right now or?
Nothing in the chat box yet. I just wanted to remind anyone that just showing up, if you have questions, feel free to use the chat box. I'll be monitoring, and we'll come to some breaks in the presentation and review those questions. Nothing as of yet. Please continue. Thank you very much.
Thank you. Yeah, I'm sure that the DWDM primer, it is a primer, right? It really encompasses the basics there. So most of you are probably already familiar, some maybe not, but anyways, the information is there. Now, what I want to talk to you about is the different instruments and how those entail. So you've all heard, and you probably all have power meters. So how does a power meter compare to a CWDM analyzer, or let's call them channel checkers? It could be CWDM or DWDM channel checkers. We have both flavors of those versus the actual optical spectrum analyzer, the OSA. So you've got your wavelength, right? And if you apply the power meter, basically what you're doing is you're actually looking at the total power that is fed through, right? So basically it doesn't really matter, it just takes a bulk of the power that's basically driven through across those channels. When you're considering a channel checker, well, basically you're looking at the power within each of the channels, all right? So you're scanning through each of those different channels. So it could be CWDM or even DWDM. So DWDM channel checkers are now available. And you can basically scan through those, and you're looking at the power per channel. From an OSA standpoint, basically what you have is you're basically scanning through the whole wavelength, and you can basically look at the power versus wavelength, and that's what it is from an OSA perspective. It's really power versus wavelength, and then there you can basically include information in terms of the signal to noise ratio and the actual wavelength. And this is where we're going to go into a bit more of details in the next few slides. All right. So we'll have a look at the different parameters and the different challenges that you need to consider in terms of the instrument. All right. So what can an OSA do? So as we've mentioned, so the OSA is basically a measurement of the optical power as a function of wavelength. Okay, so basically it enables you to measure the power of a known spectrum, the spectrum of a known or an unknown signal. You don't necessarily need to know what signal is in there because you're scanning through the whole spectrum of wavelength. Okay, as I've mentioned, it's really there to provide you a nice view of the power versus the wavelength. And by doing that, you're measuring all signal, and signal can be from noise or the actual valuable signal. So we can derive from there the optical, the OSNR, and we'll talk about that bit more details afterwards on the later slides. So the OSA really is there to give you, the whole characteristic of each of the channels, the power, the noise floor, specifically what's required when you're testing at the receiver end. It really gives you what's the tolerances of the system. Okay. Of course, the spectral profile will give you the whole signal over the wavelength range. So what are the key or the critical OSA parameters? So of course, you've got the channel power. So it's basically the laser transmits a specific output power. So it's really, you're seeing that peak power. It's the actual central wavelength. So central wavelength of each channel. So it's probably one of the most important characteristic, especially in the context of DWDM system. It really requires a great accuracy to determine, what's the actual central wavelength. And that's very important because you don't have that much leg room in terms of how much drift you can tolerate from the receiver end. Okay, so these values can be actually be monitored, and you're doing a provisioning. So you really need to make sure that you have an accurate measurement of the central wavelength. Okay, it has a major importance, as I mentioned, as the spacing between the channel bandwidth, let's say, as the spacing is reduced, well, that ability of being on the central wavelength it takes even more importance. And like I said, I'll go into a bit more detail for each of those things and why it's important in the next few slides. So channel spacing, so basically what's the separation between the channels. Typically, we're looking at channel spacing 100 gig. I was talking about 0.8, 50 gigahertz spacing. We're talking about 0.4 nanometer of separation between the channels. The OSNR, of course, is basically looking at the ratio between the signal and the noise floor, and the channel flatness. So how the signal is impacted through amplification. That's really relevant, especially in the long haul system, in terms of how flat it is, because if there's some imbalances, then that creates some other challenges down the road with regards to the how the noise affects the overall performance of the system. So here, just to summarize, so these four items are the key elements to consider in DWDM networks. So the central wavelength, the power, the flatness, and the OSNR. Okay, these are the critical parameters to consider in those DWDM networks. So central wavelength, as I mentioned, it's really looking at the actual central mass of the channel. Okay, what's the actual center? It's usually, basically, channels are typically symmetrical, so really what's closest to the peak. So the ability to be able to detect and provide a good value in terms of the central wavelength. So the higher the resolution of the instrument, the better the likelihood you will be able to detect those peaks and the separation between multiple peaks. Okay, so why test the channel wavelength? So you want to basically ensure that you are basically at the right wavelength, all right? And to make sure that if you have any drift, well, to be able to detect it and to prevent it in advance. Because if there is a drift, you can be basically not detected and you'll have a transmission failure on the other end, okay? So the receiver has a specific range that it can detect for that specific channel. So if you are close or outside, it can cause some issues with the signal going through. So in terms of CWDM filter, like I mentioned, we've got 16 nanometers. Typically, what you see, you got 20 nanometers between two wavelengths, and usually the filters will be around 16 nanometers. So anything within those, any wavelength will go in. Anything outside that will basically be blocked. Okay, so that's also one of the importance of monitoring the central wavelength.
Yeah, Hisham, there was a question from David. What was the difference between using the UPG port on the CWDM muxing and using just the 1530/1550 ports?
Just repeat the first part of the question, sorry.
The difference between using the, I'm assuming this is the monitor port or the UPG port on the CWDM muxing, and then using the 1530/1550 ports. And I'll try to find you, David. I'll unmute you if you can clarify, sir. Okay. Yeah, I think he's asking if there's a difference between using the monitor port and just using the port straight from the laser. Is that correct?
Okay, so the monitor port is really there to enable you to monitor basically with an instrument like the OSA. So you can, it's more or less a tap typically from what I understand from the question, from that monitoring port. Using the actual signal port it will be dependent, when you're using it from a measurement standpoint, is basically at the turn up. You want to you may want to verify of course the whole inspection of the ports and all that, but from an instrument perspective, you're really scanning through the whole spectrum. So the monitor port is there basically to enable you to scan all the different wavelengths. So there's a tap in there, and you'll be able to scan all of the different wavelengths that are there. So I'm not sure if I've answered the questions, but and if it's basically looking at the using a specific port to monitor or to measure, it would be more or less on the output of the DMUX. You could potentially have a view in terms of the different signals that are there. In terms of the channel wavelength, so there's different aspects that will affect the range, acceptable range of the central wavelength. So the fact that you're going through filters, ROADM, muxes, and demuxes will have an impact. So depending on the actual system, the value in terms of the range will vary. So for CWDM, usually the tolerances that you will accept are plus or minus 2 nanometers to up to plus or minus 4 nanometers. For DWDM, it's more an order of magnitude or two more stringent. So we're talking really of 0.03 nanometers or plus or minus up to plus or minus 0.05 nanometers, right? And that's really why it's so important to make sure that you have the right tool to measure those very tight spacing between the different wavelengths, so to be able to have very precise resolution bandwidth to be able to detect and measure accurately those central wavelengths. In terms of channel power, it's really looking at, in terms of definition, what's the power, what's under the curve, all right? So basically we use what we call the integration of the signal power, so the area under the curve of the signal. So why do we test for channel power? Well, basically make sure that we're within the network design specification. Is there enough power in there to reach the distance it has to reach before the next amplification stage, right? So, or to be able to be detected at the end, at the far by the receiver, okay? Because it has to be detected by the receiver. So there's some tolerances in terms of what is the minimum power acceptable at the receiver. So what we call the sensitivity. So that's why you need to make sure that you're measuring the power. In terms of the ranges, again, it really depends on the type of system that are at play and on the location of where you're taking that measurement within the system, right? So if you're looking at, at the transmitter, usually you'll be around minus 5 dBm. At the receiver end, well, basically the sensitivity will be around, minus 20 dBm or minus 25 dBm or greater than that. So it's really important to make sure that you understand the type of tolerances your system has, and to determine, at the test point, what type of power you should be monitoring at that point. Okay. In terms of the flatness, so basically the flatness is the difference between the different power levels between the highest and the lowest. So the where there's the most power and the weakest channel. So they'll give you the flatness. So it's really important because if the flatness is not good, well, some of the channels might be amplified more than the others, and that will create some imbalance with the amplifier, and will also affect in terms of the ratio with regards of the noise that is introduced at each of the amplification stage. Okay. So the channel flatness will depend on the quality of the system, and also in terms of the requirement of that specific system. And the flatness in terms of range, we're looking at basically, below 2 dB. That's where you want to be typically. We've seen up to 4 dB, but 2 dB is where you want to be in terms of flatness typically. All right.
Haisham, would it be
Yes.
safe to say that the more amplification, the more issue and imbalance that you receive on that channel flatness?
It really depends on the quality of the amplifier and what we call the gain flattening filters that are present with those ADFAs typically. So as you're amplifying the signal, you will basically try to flatten that as much as possible with those gain flattening filters at the output of those amplifiers. So depending on the quality of those, it's not necessarily the power, but the quality of how those EDFAs are built with regards to their flattening filters.
Thank you.
All right, so optical signal to noise ratio, OSNR. So this is most probably one of the most critical parameters to consider with regards to DWDM systems. All right, so what does OSNR mean? what does OSNR mean? Well, it's really the relationship between the strength of the signal and basically at all the different fluctuations that can happen. So meaning in terms of the amplitude, the phase, and the frequency, as all of these items are superimposed, collectively, all of those things, they're known and they're referred to as the noise of the system. Okay, so you're really looking at the signal, the actual transmission signal, versus all the garbage that can impact all the noise in the background of the system that will affect it. One thing to consider is that there's different OSNR methods. So OSNR can be calculated or interpreted in different ways, and it's very important to apply the proper OSNR method to the system. So it's going to be impacted by the rate in terms of it's a coherent system, the presence of ROADMs. So all of these things will have an impact in terms of what's the right OSNR method to use, and we'll go into those in a few slides from now. Okay, so there's different OSNR methods. So there's the typical IEC defined in-band OSNR. Okay, interpolation method. There's the in-band OSNR, and there's also the PUL-MOX OSNR. So where we're looking at the polarization coherent systems. Okay. If you're not using the right OSNR, if you're using the wrong OSNR method for a specific signal, the actual error that you can observe can be between 6 and 8 dB, and even more of that. We've had a customer in the Middle East that basically worked with a third-party company in terms of the a system upgrade, and they came to qualify and validate the performance of the system. And when they did the measurement with the tools that they had, they used a method to calculate the OSNR that gave them more or less 25 dB of OSNR. But the requirements, the specifications was that were required was 30 dB and 30 dB and better. Okay, so they were measuring 25 dB. The spec meant 30 dB. So what happens? Do they have to redo the work, to redo the fiber pool and all that? So they called us to validate that their measurements were okay. And when we basically looked at, okay, what type of system do you have? What are the signals at play and all that? And basically applying the right OSNR method determined that the system was in spec. They didn't have to rebuild and repull the fibers into that system. All right, it's just a question of using the right OSNR method made a huge difference there, of redoing the system. So they saved about $100,000 just by doing the proper measurement with the right OSNR method. So the importance of OSNR. So the higher the OSNR, that has a direct impact in terms of the error rate, the BERT. So it gives you a lower error rate, so lower error in transmission, and basically a higher quality of service. And if you look here at the graph in terms of the multiplexer, demultiplexer, there's like different EDFAs. So as the signal goes through the different stages, you can see the impact of each of the amplification stage on the ratio between the noise and the signal. So as you go through each amplifier, you're amplifying the signal and anything that's in there. So you're amplifying the transmission signal, but you're also amplifying the noise. And on top of that, each of those blocks, each of those EDFA blocks will introduce noise into the system. So as you go and you progress along the path of the link, you're basically impacting the OSNR. So that's why it's very important in the design and then also in the commissioning and the turn up of the system to clearly test for the OSNR at the beginning, within different test points, and at the end to make sure that the level of OSNR is within the specified tolerances of the system. Okay, the impacts of low OSNR are really, you have direct impact on the error rate. Okay, you'll have a transmission error or no transmission at all. It can be at a level where you can't even detect anything. And of course, that'll have an impact on the system performances, downtime of the system as you're closer to that threshold, the limit of the OSNR threshold or value that are of the tolerances of the system. Of course, you have a direct impact on the quality of the service that you're delivering to your system, to your customers. So in terms of the OSNR methods, so the table here really gives you an idea of how to interpret that. So let's say you're 10 gig and below, you have to consider, are there ROADMs in the systems? If there aren't, well, is it a live system or not? Doesn't really matter. You can use the interpolation method defined by the IEC, okay? If there is a ROADM, then you'll need to consider what we call an in-band methodology. So you need to make sure that the OSA is able to perform in-band OSNR calculation. Now, as you're going higher in data rates, then you have to consider if it's a coherent system or not. The presence of ROADMs in that case doesn't really matter. You can have ROADMs or not in the system. It will not have impact in terms of which type of OSNR method you need to use. What's important to consider if it's a live network or not a live network. So at what stage of the system life you're performing these measurements. So if it's a non-coherent system, even if it's a live network, you can perform and continue to use the in-band OSNR method. Now, if we're talking about coherent systems, which we're seeing more and more, especially in the long haul and the submarine networks now, then you really need to make sure that you're considering a different approach in terms of how you're measuring, calculating the OSNR. So this is where we have at EXFO developed what we call an in-service PALMOX. So within systems that are in service, we basically are able to use references and to calculate the actual OSNR, even in the context of those service systems, in-service systems. Eric, just a quick check in terms of there's any questions.
I think this slide answered some of the questions we had for that. Is there a good rule of thumb? And then I actually had a question. Can you use the in-band OSNR method if there's a ROADM or if there's not a ROADM present? Could that take the place of the IEC method, or the IEC method needs to be done if there's no ROADM? Is that safe to say, or could you elaborate more on in-band and IEC? I think a lot of our customers are looking at those two types of methods.
All right. It's really the IEC is basically very straightforward, very simple in terms of its use, and the OSA itself will tell you if there's a problem and which method you would need to use, right? So there's already intelligence in the system with regards to that, but there's no adverse issues of using the in-band across those systems, with or without the presence of a ROADM.
So
okay.
Would the in-band method be a good default method if your knowledge about the system is limited?
Absolutely.
Yeah. Okay. Good.
Absolutely. All right. So just basically, I'll do my EXFO spiel here. So there's different types of instruments in our product portfolio. And I'm using this slide just to give you an idea of, there's different types of OSA for different types of systems and different types of requirements depending on the type of technician at play in terms of what they might need. So we have the typical channel, I'll call those channel analyzers, these are the channel checkers. So we've got one for the CWDM, the 5200. The 5205 is what we call a DWDM channel checker. I have here what we call the Optical Wave Expert. It's not an OSA, of course. It's not a channel checker only. It's a hybrid. So it's really a combination of OTDR and channel checker. So DWDM, OTDR, and the DWDM channel checker. So this I'll get back to that. I have some slides, and I'll talk a bit more about that specific instrument in later slide. Here you've got the different type of OSA. So as you go up in the range, the resolution is higher. All right. So the 5255 is really for more complex systems, higher data rates. When you're talking about flex grids, super channels, subcarriers, and all these things, you really need a high precision OSA to be able to really scan and have that higher resolution bandwidth to deal with those subcarriers. The 5245 is what we call our mid-range. So there's two flavors of them. One that is basically plain vanilla 5245 that doesn't deal with polarization, but we also have one that adds a polarization scrambler, so you'll be able to use it with those types of systems. And I have a nice chart that shows that where the fit is. And of course, the 5235 entry-level OSA. So it has 100 picometer resolution. So it's a very capable OSA, but the resolution on it is of course not as good as the others in there. So you'll typically see that we've sold a lot of those 5235 with some of the cable MSOs that are deploying remote PHY. Not necessarily the tier 1 tags, but the more advanced, the Top Gun field engineers sometimes are called upon for some specific systems, and they'll usually come to the job with the system with an OSA like the 5235, right? So if we're asking ourselves what are the questions that you need to ask yourself in terms of the OSA. So what's the right spectral instrument in terms of that? So is it a system that's purely DWDM, CWDM, or is it both? What type of data rates are at play, or is it a mix? Does the system contain ROADMs? What exactly do you want to measure? If it's just channel power, well, you don't need the high-end OSA. You can potentially just use a channel checker, and you'll be able to have the power of each channel if that's what you specifically need for those for that segment of your work or on that network. Do you need OSNR? And also, there's always a question of the future. Is your system going to evolve in time? So if today you're a CWDM, but you want to add the DWDM, well, maybe going the channel checker route is not necessarily the best route. Maybe you should invest in an OSA, because then you can basically cover both CWDM and DWDM in one single instrument, right? So, and this here is the chart I was mentioning. So it's a bit of an eyesore, I know, but it really has it really helps you selecting the right instrument in terms of spectral testing, and it really answers the questions that we had in the previous slide. So if we're looking at a DWDM system, looking at just measuring wavelength and power, but over the whole CWDM and DWDM, well, you're looking at an entry-level OSA. If you're looking at systems with higher data rates, potentially flex grid, well, then you'll basically need something that has a very small resolution bandwidth or the highest precision, and you're looking there at a high-end OSA like the 5255, right? So this slide here, I'll make sure that it's available as a reference through Eric. I'll share that, and he'll be able to make it available if you want to, in terms of reference, in terms of the different instruments as the answer to the questions in terms of what are the requirements for your field testing. All right. So very quickly, I don't want to go in the details of each of instrument, but I just want to mention, we have, of course, EXFO has the CWDM channel analyzer, so channel checker. We have the DWDM channel checker. So this one here covers both the 50 gigahertz and 100 gigahertz spacing. Okay, it's a very fast DWDM channel checker.
Question on the channel checkers. Does the channel checker give you the channel for the ITU grid, or does it give you the specific wavelength that's currently being transmitted?
It's on the ITU grid.
So if you have a peak that is off off the wavelength, will the channel checker be able to identify that?
If it's off the peak, it's gonna basically more or less
Lower power.
well, the power level is going to be lower, but it's going to affect the channel next to it.
Okay. But you wouldn't be able to
All right.
identify that with the channel analyzer.
No, channel analyzer is really most of the time it's you want to verify, okay, do I have power or not? And if the power is not at the level it's supposed to be, well, that raises a red flag that you might need to do something or verify something else. All right. And it's is the channel there or not there? That's the typical first thing that you want to look for with the channel checker. And if it's there, is it at the level it's supposed to be? Okay.
Okay, thank you.
So that's all it does. Okay. Um, I'll come back to that. So we also have a new channel checker, the Max 6205. It's just 100 gigs spacing. It doesn't cover both the 50 and 100 gig spacing, but it does cover a broader range of channels. So the ITU channels 12 to 62 versus the other one that basically is just covering from around 15 to 62. So there's a few channels that are not covered by that. And so just to quickly mention it, what I want to do now is come back to this here. So the optical web expert is what we call it's not a hybrid product. It really combines the know-how of EXFO in terms of OTDR testing and combines the channel checker. And it's done on a single test board. So it's a two-in-one, more or less, capability. So it's a DWDM combo where you're looking at the an optical channel checker and the OTDR/IOLM, so the optical link mapper functionality that EXFO has introduced a few years ago. And it's the best thing since sliced bread in my view. So it's really one tool where you can basically use for turn up and troubleshooting. All right, it really is able to cover any of the C-band DWDM wavelength channels. The OTDR can actually even cover the 50 gigahertz spacing and the 100 gigahertz. From a channel checker's perspective, it's really we're just looking at 100 gig. It's really in terms of one of the key applications are remote PHY and 5G CRAN backend. So this is where it's typically 100 gig spacing what we're seeing in that space. Okay, and you can define pass-fail threshold. All the diagnostics, and as this is a new product, we're adding more features into it where to provide more intelligence and link between the actual channel checker and the OTDR IOLM application. So in terms of the different applications, well, DWDM link characterization to the muxes, DMUXes, and the ROADMs, the link troubleshooting, so at the DAA, the remote PHY, or the CRAN, as I mentioned, the newer Metro Ethernet link based on DWDM, so be able to characterize the performance of the link. More and more now we're seeing lambdas being deployed for specific business services, so be able to have a tool. And this is basically where you're looking at, usually, or in the past, the last mile fibers that went to the home or went to the business, it was a drop fiber. So the value in there or the impact was less significant. So the dollars associated to that link was not as significant as, oh my God, if the link goes down or there's an issue on the long haul link, well, you're impacting multiple customers upstream. But now as business services and as you're pushing, the value of that last mile fiber is increasing more and more. So having the right tool in the hands of the people out there in the field, it makes a big difference. So that two-in-one combination really talks to those possibilities of empowering a bit more the field teams as they turn up or troubleshoot those segments of the network. All right. All right, I talked about this. So in terms of the different OSA, so the 5235 is what we call our entry-level OSA. It's really compatible across the different value of the EXFO test platforms. So most of you might already be familiar of those. OSA. So I've talked about the 5245. So it's our mid-level OSA. So there's two flavors of it. There's one with, this one is without the polarization scrambler. So what we call, and this one is more or less, it's suitable for lab manufacturing in the field. It supports multiple types of software options like WDM Investigator, commissioning assistance, and of course the advanced optics. So we're looking at drift of transceiver and things like that, more in the NEMS space. And next one is what we call the high-end optical spectral analyzer. It's really looking at, it covers the different OSNR methods. It really is the workhorse, future-proof instrument in terms of our catalog. Just want to make sure that we have enough time to answer any questions that you might have. That was my last slide in terms of the EXFO spiel on our product portfolio. I don't know if there's any questions, comments with regards to the portfolio or the different technologies.
I do have a couple, Hisham. Todd Baxter was asking specifically about their campus, multi-campus DWDM network. They have about 40 channels muxed at each location, and they cross-connect the different channels through those muxes. What would be the best way to troubleshoot an individual DWDM channel for open or missing jumpers? And I think there might be a couple options depending on the equipment available. But could you speak to that?
So to missing jumpers that I heard.
Yeah, I think he's looking for any jumpers that may be missing in the cross connect through the muxes, and I'm thinking maybe a channel analyzer would allow you to see if there's power.
Yeah, exactly. Yeah, exactly. So in this case, you don't need anything. You're not necessarily looking at the spectral or OSNR. You're really looking at is the channel provision, is the light going through. Is that channel specifically being routed? So a channel analyzer, a channel checker will do their job for that in terms of being able to detect those issues at specific channels. If there's a jumper missing, so that channel is not going through, the channel checker will basically be able to scan through the whole channel plan and will show point blank, oh, I'm supposed to have this wavelength, this channel, this ITU channel, I'm not seeing it. Okay, there's a problem, and that would be the ideal cost-effective, let's just put it that way, tool for those type of situations.
Okay, follow-up question for that: would we'll say like a 740 or an OTDR that can dial down to the specific wavelength, would that be able to identify where specifically the break would be? I guess that would be kind of, or where the end of that signal would go. Would that be a good use case there?
Yeah, absolutely. So if you see that there's no signal there, then basically okay, at this wavelength I'm supposed to detect something. So you can then use the OTDR or the RLM to basically at that wavelength shoot make the OTDR trace, and it'll give you the location of the potential of where the fault is. So at which point it is. What you need to be mindful of if your system has the transceiver at the end, transmitting, to make sure that you're using a safe mode to make sure that you don't impact the optics on the other end, right? So the EXFO equipment has that capability. So with the IOLM, you can have the safe mode option, so you make sure that you're not impacting the transceiver on the other end, because some of them are a bit more sensitive. When you're shooting with the OTDR, so you basically have a signal that's going through the link, so you make sure that you're doing that properly. And the optical wave expert, meets the bill to address that type of use case.
So that was Todd's next question. Would the 740C work for that? I was going to suggest that you might be in the market for an optical wave expert, Todd. Definitely an interesting unit that would address specifically the issues you're discussing. If you have a 740C, a channel analyzer, in addition to that, may help you identify which channels are problematic. Let's see. Any other questions? I wanted to go back to David's question. David, are you available, sir? I'm going to unmute you. David, you're unmuted.
Yeah.
Go ahead.
Yeah, thanks. I just wanted to make sure if there's a big difference between using the upgrade port in the MUX, CWDM MUX, to using the 1530 or 1550 channels when adding a DWDM.
All right, so my understanding is that the upgrade port is basically if you want to add additional CWDM channels, meaning that you have another possibility of adding some of those CWDM wavelength to your system. Unless I don't understand how it is, but with the hybrid system, you're really using that same channel, let's say 1330 or 1530 or 1550, and you're basically out of the DWDM MUX, you're entering that CWDM MUX at that channel. So all the example I had, we had 19 wavelengths, so they're all within the passband of the filter for that specific 1530 or 1550 channel.
So you have your DWDM channels within your CWDM MUX, correct?
Exactly.
Does that make sense for you, David?
Yeah, so you're saying that there's not much big difference between the two, using the two options.
Like I said, for me, it makes more sense to use the direct channel of that CWDM wavelength. So through that channel port, this is what you wanna use, because it avoids of having any risk of having two signals at the same wavelength being muxed in the system and creating some issues there.
Great. Thank you, Hisham. David, thank you, sir. Any other questions for Mr. Hisham while we've got him? If anything comes up in the interim, feel free to email myself or any of the SNS folks. We'll direct your question if we can't answer it. But and if you're looking for any specific training on your EXFO units, you can also address that. Yeah, I will be sending out a link to this recording. And looks like there's been some request for the presentation. I'll see what we can do on getting a PDF version. There's definitely some reference slides that I want to put together for everyone. So, let's see, any further questions from anyone? You can use the chat box. All right. Well, if no further questions, I'm going to go ahead and come to the end here. We're right at 11 o'clock. Wanted to say appreciate everyone for attending, and we'll be doing these at 10 a.m. on Wednesdays. If you receive the login information, we'll talk to you next week, where we'll have Fitel and introducing the new S124M12. And yeah, thanks very much, everyone. Have a good week, and we'll talk to you soon. Hisham, thank you, sir.
Everybody,
really appreciate it. It was very informative.
Thank you for the opportunity, and have a good day, everybody. Stay safe.
Thank you.